Alright folks, this video is intended to be viewed after the two hypothesis test examples, but I don't blame anybody if they went and looked at a couple more run-throughs of that process in the practice quiz or in the book or anywhere else. That is the most important thing to keep in mind because again, those 5 steps, they're going to be haunting your dreams by the end of this thing because we are going to be using them just in a variety of different contexts. All that's going to shift is how we get that information that we need to get in each step. So get that pinned down as early as possible. It will make the rest of the course much smoother. So in any hypothesis test, z-tests, which we're learning about now, or any other one, at the end of the hypothesis test you make a decision. And the decision is between one of two choices, which is to reject the null or to fail to reject or retain the null. And again, we designate that area where we reject the null as what's called the region of rejection. The size of it is based on the alpha level, as are those threshold values that make up the borders of it. So here we have a comparison distribution again, and I've marked it up as a two-tailed test because that's the most common. In the two-tailed test, we can reject the null either for scores that are well below the mean of population 2 or well above. Both of them let us reject it. Anything in the middle, we retain it. Here's the thing. The decisions that we make, again, are based on probability. They have to be because we are making decisions about large numbers of people we didn't measure in that entire population. So there always has to be uncertainty there. When we reject the null, what we're saying is there's a small probability that these results would happen if the null was true. That's a small probability. It's not a zero probability. Remember that tendency in probability we talked about where people round small probabilities down to zero? They just think of them as zero. No matter how small that probability gets, it is not zero, which means there is always a chance that we have made the wrong decision, that we rejected the null, but the null was actually true. There really wasn't anything going on in the populations. Conversely, when we fail to reject the null, we may have, in fact, a significant result. There may really be a difference in the population, but our studies just weren't likely to find them. Remember that idea of power? Powerful studies will find significant effects that are real. So if our study is not very powerful, or if we just get a fluky sample, we might wind up failing to reject a null that we should have rejected. It was actually false. So no matter what decision we make, and again, this is hard for people to get their heads around if they're used to math classes. People are used to certainty in math, that if you do things right, you will get the absolute right answer. Because we are drawing conclusions about those much larger groups that we didn't measure, there's uncertainty there. Even if you do every single thing right, you are guaranteed to make some mistakes over time. You minimize that number, you can get it to be pretty low, pretty improbable. You never, ever make that number zero. You are guaranteed to make some mistakes if you run enough hypothesis tests. Because again, it's not because you did something wrong, it's because the data wound up in a form that wound up being misleading. So here's what can happen. When we reject the null, we could be making what's called a type 1 error. And you may have heard of a type 1 error called a false positive. This is what happens when the null hypothesis is actually true, but we find strong enough evidence to reject it. Again, this can happen without you doing anything wrong as a researcher or as a statistician. There's no real effect, but we got strong enough amount of data to falsely conclude that there was. So here's an example of a false positive. It's kind of funny. Homer Simpson's here. His doctor is telling him that he appears to be pregnant. In reality, he's just overweight. So the false positive there in that case would be that they determined that he was pregnant. They rejected the null hypothesis of not being pregnant, and that turned out to be a false positive because he just is a large dude. So when we reject the null, we could be making these type 1 errors or these false positives. So type 1 errors can happen anytime we reject the null. Here's the nice thing about type 1 errors is we know exactly what the overall probability of a type 1 error is. It's exactly the same as alpha. Here's how it works. Remember alpha, when alpha is 0.05, we say, okay, alpha of 0.05 means there's less than a 5% chance, a 5% or less chance that these results could happen if the null hypothesis was true. But there's still a 5% chance that you could get results in that region of rejection if the null is true. So you know pretty much as a guarantee that about 1 in 20 Statistically significant results where you rejected the null is going to be a type 1 error if you have an alpha of 0.05. How can you fix that? Set a lower alpha. If you set a lower alpha level, the region of rejection gets smaller, the critical values get farther away, it's harder to reject the null, and now your, again, likelihood of a type 1 error is going to be about 1%. You could set it even lower than that and keep going, but again, those two are the typical pattern. So whatever your alpha level is, that's your probability of a type 1 error. Type 1 errors are really, really bad in science because we invest resources, energy, time, our reputations on significant results. If those results turn out to be erroneous, even if it's not any fault of the researcher, you're going to waste a lot of time and effort, and you probably are not going to be as highly regarded as you would if your findings held up consistently. Here's another thing. A lot of studies are pretty complex, and they might involve dozens of significance testing. And we have computers do this. We don't do it by hand. We're not sitting down writing out the 5 steps, for just tens of hours a week. But here's the thing. When you run a lot of significance tests, a lot of hypothesis tests, all at the same alpha level, the odds that at least one of them is a type 1 error starts to get awfully high. With enough tests, it starts to approach 100% that you're going to have at least one type 1 error. Here's the kicker. You look at that, you run your dozens and dozens of tests, you look at the significant results, you can know there's a really good chance that there's at least one type 1 error in there, but you don't know which one. You have no idea which one. That really strips a lot of confidence away. You also don't know if there is one. Maybe none of them are type 1 errors. Maybe 2 of them are. So those are both less likely than one, but again, those are possible as well. So when you look at a set of results and you're almost certain one of them is a mistake and you don't know which one, that's a bad place to be as a scientist. That's a bad place to be in fields that value certainty of findings. So those are type 1 errors. And again, those can happen only when we reject the null. That's the only error that can happen when we reject the null, because it's all about rejecting the null and being wrong. Now, of course, we have a second error, and it's very cleverly named the type 2 error. I'm sorry, statisticians aren't real creative. You can think of it as a false negative, and that's a totally valid answer too. Type 2 errors can happen when we fail to reject the null, or when we retain it. So type 2 happens when there really is a difference between the populations and we fail to reject it. Again, not necessarily because we did anything wrong, but just our sample wasn't a strong enough pattern. It wasn't far enough away from the population 2 mean to be in those regions of rejections. So there's a real difference, but we didn't get a strong enough pattern of data to conclude that there was. So we failed to reject the null, and the null was actually false. So here's an example of a type 2 error. You're not pregnant. This woman clearly is. They failed to reject the null of her not being pregnant. They didn't find a strong enough pattern in the data or not. The probability of a type 2 error is denoted by, this is beta. So we have alpha for type 1s, beta for type 2s. We haven't seen beta before, but we have seen the concept it's related to. Beta is inversely related to power. What that means is that the higher your power is, the lower your beta is. Think about it this way. If the null hypothesis is actually false, if that's actually what's happening in the population level, there's only 2 things that can happen at the end of a hypothesis test in that case. One, you can correctly reject the null hypothesis. The likelihood of that is your power. The more powerful a study is, the more likely it is you can correctly reject the null hypothesis. 2, you can incorrectly fail to reject the null hypothesis. Notice that's the definition of a type 2 error. So the only 2 things that can happen when that null is in fact false is you can correctly reject it or incorrectly fail to reject it. One of those, the first one, is power. The second one is type 2. The more powerful your study is, the lower the risk of type 2 errors are. So we've talked a little bit about power before. We're going to talk a little bit more about it now because it's relevant to this. Here are some things that can increase the power of your studies. One is you can have a bigger what's called effect size. And you can see the next talk for what an effect size is. But basically, a bigger effect is one where the population means are farther apart, so it's easier to find a result that's in the region of rejection. You can't control that one. You can't make things have higher effect sizes, but you can try to study things that you expect have higher effect sizes. You get more powerful designs then. Measure more people. Notice that's kind of a cure-all for a lot of problems. Get more data. Measure more people. Or we could set a higher alpha level. If I increase this alpha level of 0.05 to like 0.10, my regions of rejection would get a little bit bigger, right? A little more space there. There's a little more room. It's a little easier to reject the null overall, so it's less likely that we will fail to reject the null when we should have rejected it. But what's the trade-off? You should already be able to figure it out, but the trade-off is more type 1 errors. Alpha is linked to both of those. So the easier it is to reject the null, the more likely it is that you're going to falsely reject the null. You're going to make a type 1 error and reject the null when you should not have. So alpha level is related to both of those. Higher alpha levels, you get more false positives because it's easier to reject the null, but fewer false negatives because it is, again, easier to reject the null. It's harder to retain it. Lower alpha levels have the opposite problem. More type 2 errors because it's a higher bar to reject the null, fewer type 1 errors. Which one do we tend to pick? Scientists tend to avoid type 1 errors. We really don't like those false positives because, again, you wind up investing a lot of time and resources and reputation. In other fields like medicine, a lot of times you will try to avoid type 2 errors. A lot of screening tests for diseases will deliberately have a large alpha level. The reason why is they want to catch every single person that has that disorder, even if they're going to take a lot of false positives to do it. So, for example, a lot of screening tests in pregnancy for possible fetal disorders, they'll warn you, if you test positive on this screening, there's still over a 90% chance that there's nothing wrong with the kid. The reason why, again, they want to cast a really wide net, because their emphasis there is don't let anyone who has these disorders slip through this net, because it's really important that we treat them. So we want to make sure we catch everybody, so we will take a ton of false positives for that to be the case. So medicine oftentimes makes a different decision than science does. In science, we're willing to take a lot of type 2 errors if it reduces our type 1s, because we really want to be confident when we reject the null that we're doing so accurately. The other thing to note is we've talked a bit about research methodology. Bad methodology will make both of those errors more likely. Bad methodology is a killer. Always make sure your studies are well designed. So here's a little grid in emoji form. So let's say that we have an actual situation, what's actually happening in the population. Maybe the null is true, there's no effect, there's no difference. Maybe the alternative is true, there is an effect, it means the null is false. And then we have our own decisions, rejecting the null or accepting, failing to reject the null. If the null is actually true and we reject it, we have made a type 1 error. So we rejected the null and it was the wrong decision. The probability of that is marked by alpha, and the result is sad face. If the null was actually false, if the alternative was true and we rejected the null, we made the right decision, happy face. This is all very technical stuff. If the null is actually true and we wind up accepting the null, again, we made the right decision. We failed to reject the null, but the null was true. If we accept or fail to reject the null, but the null is actually false, there really was an effect there, we've made a type 2 error. The probability of that is beta. Again, it's the opposite of power, and the resulting emotion is once again frowny face. Stay away from those frowny faces. But anyway, again, we can minimize the probability of these two things happening, but oftentimes there are trade-offs. Things that lower the likelihood of one error will raise the likelihood of another, and you will never, ever, ever get those probabilities down to 0. So the idea is you want to strike a balance there with an acceptable amount of uncertainty. But the uncertainty will always be there because you know that not only are errors possible, over a long enough period of time, they are inevitable. All right, this is our second point of emphasis. Again, our decisions can always be wrong. Sometimes you get fluky samples that wind up in the tails of the comparison population, even if there's no difference between the populations. That's what's known as, again, a type 1 error. Or there is a difference at the population level, but your sample wasn't extreme enough to be in that region of rejection. That's a type 2 error. This is especially likely if you don't measure many people. Type 2 errors get very, very likely when n is very small. We can never prevent them, but we can reduce their likelihood. We can account for them in our thinking. The biggest way we account for them is uncertainty and a desire to replicate effects, to show them again and again. So good methodology can help reduce both of them, appropriate alpha levels, and keeping that uncertainty of your results in mind. That's the end. Next time we'll talk about effect size and some future directions where the field of hypothesis testing might be going. And we'll put a wrap on this module.